All right, legends, welcome to the 7.2 video notes, the long-awaited 7.2 video notes, which of course are focused on significance tests for specifically proportions. Just to be sure and to recap a little bit, you should go through and you should have up your 7.2 slideshow presentation to refer back to. Also be sure to give a look to the 7.1 video notes if you're struggling with sort of the theory behind what p-values are, what type 1 and type 2 errors are, what power level is, and what the alpha is, because these sort of overarching concepts, I should say, are going to be super important to us when we delve into doing actual calculations for significance tests, and in the example for 7.2, learning to apply those to proportions. Now, just like with confidence intervals, we're really only going to be doing, one sample z-tests in this case for proportions, and then 7.3 will be one sample t-tests for means, right? So it's the same concept as last unit, and in fact, a lot of the processes are similar, except in this case, we're gonna go through the components known as phantoms. Ooh, now you may remember from class, I dress up as a phantom, by which I mean I grab an old bedsheet, tear a hole in it, throw it on myself, and do bizarre, wicked dances. Well, I remind you of the components required to run a significance test. Now, a couple of key things to note here. On your 7.2 slideshow, on slide 3, we break down every aspect of phantoms. And what are these aspects? Well, they are identifying the parameter of interest, then offering your hypotheses. The hypotheses will be the null and the alternate, right? And this should be in your mind, again, from the 7.1 video notes. We then run our assumptions. That should be in your mind from confidence intervals. It's the same set of assumptions because we're using sampling distributions to make our theories about tests for hypotheses, just like we did with confidence intervals. Then, of course, we name it. We got to name the test. Right? Then we do the test statistic calculation. And the test statistic calculation is just where we go through and we find the actual values, which we'll see today. From that test statistic, you need to obtain the p-value. Now, as you'll see, if you're just doing it all in the calculator, the test statistic calculation and the obtaining of the p-value is all one step. But if you're doing them separately by hand, you obtain the test statistic. That's the z-score for your sample proportion in reference to the reality where we treat the null proportion as true. And then you will obtain the p-value. And the p-value is calculated, of course, by taking the test statistic, the z-score that we get for that, and then finding the odds of a value that extreme or more extreme on a normal curve in the case of proportions. And then M and S come together as make a conclusion, which we'll see in a moment, and then state in context. Now you'll notice that a lot of this is just adding extra words, and that's because we wanted it to spell phantom so I could do my little shtick. But each component here, oh, it's cool. It looks like kind of the scroll from Star Wars, but it's all going downward. All right, Mr. Mays, let's make relevant quips, shall we? But all of this is to say, it's essentially the same process we had for panic. So let me walk you through this process. And actually, let me walk you through this process with this above example. So I'm going to go to my favorite color, purple, and we're going to use that. Actually, let's use like a fuchsia pinkish thing going on here. Ooh, this orange. Ooh, guys, wait a minute. Okay, wait. Let's go wild. Let's go. No. This is what I want. I want this like deep, rich purple. Okay. So I'm going to run through panic with you. I think or phantoms, I should say, with you. I think this is the best way to do it. And as you do it, you can look through at the slideshows, but let's solve this problem together. So it says, a simple random sample of 1,028 U.S. adults in March 2013 found that 56% support nuclear arms reduction. Does this provide convincing evidence that a majority of Americans supported nuclear arms reduction at the 5% significance level? Now, when it says, does this present convincing evidence or provide convincing evidence, that's when you know you're going to do phantoms, right? When they're asking for convincing evidence for something, we're normally doing a hypothesis test. So, a couple things we should know. Let's go in order. Let's start with phantoms. Step 1 of phantoms in this case will be identifying the parameter. And the parameter of interest here is support of nuclear arms reduction. So we'll start out with true proportion, because of course we're working with proportions, of, let me see if it says Americans. Yep, US adults. Who support nuclear arms reduction. And lo and behold, my heroes, my legends, you've already done a chunk of the process, right? M and S are really one step, so it's really 2, 4, 6, 7 steps. You're 1/7 of the way there. So we are identifying what we're doing. We're looking for the true proportion of U.S. adults who support nuclear arms. I'm thinking every time I see U.S. adults or like U.S. Population, I think of that like. I don't know if you guys were too young for this, but there was a really silly video that made its rounds on YouTube about like Miss South Carolina getting asked about aid in the world and in Africa, and she kept saying U.S. Americans think, and it was hilariously reductive. Okay, we've got our parameter of interest, the true proportion of U.S. adults who support nuclear arms reduction. Step 2 of phantoms. We have to state our hypotheses. Now, you should have this down to a science after your practice and after what we had with 7.1. But let's try and work this out. We're going to have a null hypothesis, and we're also going to have an alternate hypothesis. Now, the null hypothesis will be always P equals something, okay? So going to our initial question, it says that a random sample of 1,028 results found that in March 2013, 56% support nuclear arms reduction. Now that's a sample, so I already know that's not going to be what I'm looking for when I'm going in to look at my hypothesis. I'm looking for the argument. It says, does this provide convincing evidence that a majority of Americans support nuclear arms? I like this question because it makes things more difficult. Normally the null proportion will be stated, but it says a majority here. A majority is anything greater than P. So that means our null, or 0.5, I should say, 50%, greater than 50%. So that means our null proportion is that the hypothesis for the null is that the p-value, or I should say not the p-value, the proportion, the null proportion and the true proportion are equal to 0.5, okay? So 0.5 will be equal to the true parameter if we are wrong. But if we are not wrong with our alternate hypothesis, p will be greater than 0.5, okay? Note that we always use the null proportion for both the null hypothesis and the alternate hypothesis. Okay, we've already gotten through some difficult stuff here. We've taken and broken down the language of the question. We've determined that the majority of Americans signifies that our null and alternate hypothesis circulate around this 0.5 proportion idea. Okay, and wisely to the side, you've already noted your p-hat value of 0.56, okay? But before we do any work with that, we've done the big first 2 steps. We're going to move on to assumptions, and assumptions are going to feel like old hat to you because you've already done these. They are the 3 assumptions you had to do for confidence intervals for proportions as well. So let's walk through these with each other, shall we, my heroes, my legends. 1, is it random? In fact, it is random. It says a simple random sample. So we can just say that that is stated in the question. Okay. Why does it have to be random? We need the sample to be representative. We need to make sure it actually shows up for U.S. adults. And we're good to go on that. Second step, is it independent? Why? If any dependencies arise, as we saw in class with the being able to taste Dr. Pepper experiment, we could get a uniform or a multimodal trend out of our sampling distribution, but we don't want that. We want what we got with our guessing trend, where we just guessed blindly and we had a perfectly normal distribution with no dependencies. For that to be the case, the population, the entire population, must be greater than 10 times the sample size. So what we would state here is that 1,028 times 10 is less than the U.S. population of adults. And we can assume that. We can just state that that is the assumption. One little issue that I noticed on some of your confidence interval exams was that you thought that the population problem, the whole 10 times the sample size, was proof of normalcy. And this is not. This is proof of independence, because what we're actually saying is not that we want a large sample size, it's that we want our sample size to not be too large. That was another tiny mistake I saw. Every once in a while, a student would say the population has to be less than 10 times the size of the sample, and that's not the case. We need 10 times the size of the sample to be less than the population's total size. Because if it's too big of a sample, we're going to start to get big picture dependencies that we don't want to mess with. All right, and just like we saw with confidence intervals, we're going to go into the third step, which is we need it to be approximately normal. What do we need for that to be the case? Well, as we know, n times p. In this case, it will not be p hat. It will be the null proportion. Why? Because as we know from the 7.1 video notes, our entire sampling distribution is with the assumption that the null is true. What we're going to do is use our sample to disprove the null on its own terms, but to do that, we have to treat the null proportion as the truth. So n times p null must be greater than or equal to 10, and n times 1 minus the null proportion must be greater than or equal to 10. Those are our two rules, and they are absolutely lovely. Okay, so for the case of our problem, we've already stated 10 times 1028 is good, random is stated, and our null proportion here is 50%. So lo and behold, 1028 times 0.5 is in fact greater than or equal to 10, and 1028 times 1 minus 0.5, which is also just 0.5, is greater than or equal to 10. So we are good to go on that front. Let's go over to green for a second. Check, check, okay, check, and check. We've hit all of our assumptions. We are the heroes that we always knew we were meant to be. Oh, I'm so proud of us already. Okay, deep purple. Let's keep on rolling. We've hit our assumptions. We've got our hypotheses, and we've made our statement of what the proportion parameters we're looking for. Okay. You'll notice up until the end of assumptions, we haven't even touched our p hat. And I want you to note that. You don't need your p hat all the way through the p, the h, or the a. We don't even touch the p hat until we get past the n even. It's at the t that we're finally going to use the p hat for anything. What is the n? That's just naming our test. In this case, and always with proportions, it will be a one sample z-test for proportions. A one sample z-test for proportions. And we're set. We've named our test. Okay, we're finally going to get to use that p hat. If we move over to t, that is where we find our test statistic, aka the z-score that our p hat would have, and this is the long-winded way of saying it, on the normally distributed sampling distribution of the null proportion. Okay, that's a lot of words, but what I'm saying is, in a world, actually let me get rid of the period here, it's kind of getting in the way of the null there. In a world where we have the sampling distribution of the null proportion, which we set up with P, H, and A, mostly with A, I should say, with our assumptions. In that world, we want to know where on that distribution our p hat would sit. And if it's extreme enough, that tells us, hey, this p null, the null proportion, cannot possibly be correct, because I would not get a sample proportion, a p hat, as extreme or more extreme than mine if that were the case. We'll do this by comparing to the alpha. Now in this one, it says our alpha is 5% significant, so we know our alpha is 0.05. We're going to keep that in the back of our head. Now you don't have to state any of this part here that I have written down. This is just me to remind you, or for me to remind you, I should say, hey, that's what the test statistic represents. Here's the equation. Z equals X minus mean over standard deviation. That's the normal z-score equation. This one is effectively the same thing, but what it's going to entail is instead of x and the mean, we're going to use p hat and compare it to the null proportion. This way, because we're subtracting the null proportion, if p hat is smaller than the null, we will yield a negative z-score, which is good. It'll be to the left of the null proportion. If p hat is greater than the null proportion, which is the case in this example problem, we'll get a positive z-score, and so our p-value for the p hat will be to the far right. Really quickly, I'm going to sketch a little graph for you so we can see what we're talking about here. We are to assume that the null proportion is right in the center. And we're going to identify, in this case, we're hoping that, according to the alternate, that the p hat is greater than 0.5 or greater than the value. So we're hoping that on this distribution of null proportions, our p hat is somewhere way off to the right. Because if it is, there's less area under the curve that's that extreme or more extreme to the right, and that will yield a small enough p-value, and that p-value will prove to us it's so unlikely that the null proportion is true and that we can reject it. Okay. Just want that sitting on your side. Again, none of that has to be drawn when we're doing the test statistic. Just want you to understand the theory behind it. Okay, I'm going to erase that now. Let's do our magic, shall we? Ooh. Boom. Okay, it is our p hat minus the null proportion over the standard deviation for the sampling distribution, which is, again, the sampling distribution will be for the null hypothesis, therefore the null proportion, but it's just null proportion times 1 minus null proportion, so success times failure, over the sample size n. Now, I'm going to follow this through to show you how to do it by hand, okay? This will be the way we calculate this by hand. We will do the test statistic by hand, and then, lo and behold, we will do the O of obtaining the p-value by hand. But then over here in the corner, I'm going to write out the calculator method. And the calculator method for all of this, where you just put the whole thing in the calculator, is going to handle T and O. It will do both steps for us, okay? Over here on the right. And actually, let me get rid of the circles around those because it makes it hard for them to be read, right? And we can do this when we just need the outputs, we just need the values, and we are not concerned with the equations. But as you've seen in the confidence interval problems I give you sometimes, and that AP gives you sometimes, you do need to be able to see this method here as well. So be prepared for that. Okay, this would be our setup. So that means for this particular problem, our p hat is 0.56, because that is the sample proportion we got from the problem, 56%, minus 0.5, because we want majority, over square root of, again, null proportion, not sample proportion, 0.5 times 1 minus 0.5, over 1,028, because that was our sample size. Now, you could have rounded this, any number of ways. I just want to math this through with you really quickly. What I end up yielding, and actually I'm going to give myself a little more room below this obtain, is with rounding. Now, you could put this whole thing in the calculator, but when I round, what I do actually is I do this denominator first, and what you get for just the denominator, aka the sampling error, right? The standard error, I should say. For just that part, you get, if you round, about 0.016. And then what that means is the z-test statistic will equal, right, 0.56 minus 0.5 over 0.016. I don't like to plug the whole thing into the calculator. Again, I like to do this denominator, also known as the standard error first, right? That's what I do over here. I do this. And then I like to swap over, and at the end, I bring in the numerator, and I put it up against this denominator. Just keep track of your components. It should all suss out. You then can run the calculation, round accordingly. You should get something in the ballpark of a 3.75 test statistic. In the ballpark. If you get a 3.84, that's okay. Again, just show all your steps. So that's our test statistic, aka our z-score is about 3.75. You should already know that you have won. You get to reject the null. Because if you imagine a sampling distribution with the null proportion in the center, this is not 1, not 2, not 3, but almost 4 standard deviations to the right of that value. There's simply no way that the null hypothesis has a chance here. We are going to reject the null, I guarantee you, okay? But just to make sure we understand how to do this, we will obtain, right, the p-value. Now, remember, if the alternate is that the p-value, or the proportion, no, not the p-value. Mr. Mays, don't be silly. If the alternate hypothesis is that the p, the parameter, is greater than the null proportion, that will mean that we will do lower bound as the z-score, the test statistic, upper bound as 100,000. Why is that? Well, if you were to imagine the standard distribution with the null proportion in the middle and a p-value to the far right, a z-score for the far right for the p-value, we are imagining this extreme or higher, right? Greater than, which means we want the lower bound to be the z statistic and the upper bound to be 100,000. On the other hand, if the alternate hypothesis is that the p-value is less than the null proportion, we do the exact opposite. The lower bound will actually be negative 100,000. The upper bound will be the z test statistic, right? Again, because that version would be something like this. We're arguing that the null proportion is here, the p-hat is to the left of that, and we want the value to the far left of that distribution. If on the last hand, we have a two-tailed test instead of one-tailed, be aware both of these are one-tailed. If on the other hand, we have a two-tailed, which you'll know because it'll say, the alternate will be that the p, the parameter, is not equal to the null proportion. What we will more likely than not do, and it will depend based on the problem, but we will more likely than not do is we will treat it like we do the one-tailed for greater than, right? You'll take the formation, the null proportion, you'll find the greater than value, right? And then you'll just do times 2 because we want to find this end and the upper and the lower end. So we'll do times 2. So normally it'll be 2 times, and then we'll do the calculation for lower bound z-test statistic, upper bound 100,000. And we will do this where the z-score is absolute valued. So if you get a negative value for your z-score, just absolute value it. Why is that? Well, you could do it the other way around. If you get a negative score, just do this one, the one where it's less than, and then double that. Just be aware that if you get a negative z-score, you're looking at the lower tail. And if you get a positive z-score, you're looking at the upper tail. So whichever one you do, be aware that you should set it up according to that, either the lower or the upper, and then just multiply it by 2 to get both the upper and lower values. Okay, that was long-winded, but all of this is to say, hey, lucky day, we have a greater than test statistic, so we're going with this one. So let me outline that for you. Let's do blue for this. We are stating that we want our p-value to come about. We want to obtain that p-value. We have, right, a z-test statistic of 3.75-ish. So what you will do is you will do normal CDF. Lower bound will be the z-score of 3.75. Upper bound will be 100,000. Mean of 0, standard deviation of 1 because we are working with a z critical value. I get a value of about 0.0001. A very small number is the key here. You may get something a little bit smaller than even that, but I round it to about 0.0001. Okay? We've done the heavy lifting. We've obtained the value. Now, I want to make this very clear. The other thing you can do if you don't want to do all this by hand, or if you are enabled to not do this all by hand, is you can do the fully calculator method. We go to stat, right? And frankly, you know how to do this. Let's be real here. We went over it in class. You're going to run this like it's a marathon, but let's just be clear. You go to stat, you go to tests. What test are you going to do? Well, of course, one prop z test. Put in your null proportion. In this case, your null proportion will be 0.5. Put in your x, which is number of successes. Put in your sample size, which is 1,028. Now, in your case, our sample gave us 56% of that, right? So what we'll do is we'll do 1,028 times 0.56. And that yields 575.68. We need a whole number for people, so we'll say 576, okay? And that'll do just fine, right? Excuse me. So we have all those inputs set. They're looking gorgeous. The last thing is it will say prop, and you will choose. And in this case, the alternative proposition, right, or the alternative hypothesis, I should say, is that the p is greater than. So for this one, we will want to do the one where it goes greater than null proportion. We fix that little dot so it's an O. Okay, and you'll run that entire thing, and it will literally give you the z critical value. It will give you the p value. It'll give you everything you seek, okay? So that's available to you as well. So we go through, you either have done this test statistic calculation followed by the p-value obtaining, right? Or you've just gone and thrown it all into the calculator and calculated it accordingly. And we have our p-value. Now we have the last set of steps. Let's do this in green because we feel good about ourselves. M, which is make the conclusion. What does that look like? Well, let's see. In this particular case, we are going to compare the p-value to the alpha. Let's do this, okay? Our p-value is 0.0001, something like that. We are going to note that that is less than the alpha, which is equal to 0.05. So you will do 0.0001 less than 0.05. Therefore, we reject the null. Therefore, there is convincing evidence. And this is where we give our context, okay? So actually, I'm going to put this here. State in context. Right? So to be very clear, I'm going to use my blue highlighter. So for making the conclusion, that's what this is. Right? Comparing the p-value to the null. For stating in context, that's what I'm about to do. There is convincing evidence for the alternate hypothesis which is that a majority of U.S. adults support nuclear arms reduction. Lo and behold, that is our context provided. Okay? You must do this. It is so important. And actually, making the conclusion includes rejecting the null. Okay? That's actually all in there, I should say. You can barely read reject the null. Okay, so one more time for the cheap seats. Let's go through everything we've done here because it's really, really, really cool and super impressive. From the top, we've learned phantoms. In this particular problem, we have walked through every step required to solve a hypothesis test for proportions using a normal curve and a z-test statistic for one sample. So we took a look at our problem. We noted our alpha level and we noted our sample statistic and everything that we can roll with. We've gone in. We've set our parameter. What is it? The true proportion of U.S. adults who support nuclear arms reduction. We've set our null proportion and null hypothesis, which is that the parameter is equal to 0.5. Why? It says that we want to use convincing evidence to show that a majority. And to set that majority, the null proportion that we're fighting against is not a majority. What is not a majority? 50-50, right? Split down the middle. So the null hypothesis will be that the parameter is equal to 0.5. The alternate hypothesis, on the other hand, is because we want a majority, not a minority, it's that the parameter is greater than 0.5. Notice again that we use the null proportion in both the null and the alternate hypothesis. We then go through our assumptions. They are the same heroes, legends, as they were for confidence intervals. Is it random? Yes, it's stated. Is it independent? Yes, the 10% rule applies. And is it approximately normal? Yes, the large counts condition is met, right? N times P null, not P hat, P null, and N times 1 minus the null proportion. Excuse me, and that has been met. You see our cute little check marks. We name the test. What is the test? One sample z-test for proportions. Similar to confidence intervals, but a different thing we are doing. Now, you have two options. One, you can just do the calculator method. This takes care of both T, test statistic, and O, obtaining the p-value. You go into stat, you run your tests, one prop z-test, you do the null proportion, in this case 0.5. You look at X, your success rate. What I did was I took my p-hat and I multiply it by my sample size N and I rounded up, right? So I got 575.68. I went for 576. My N is the sample size, 1,028 in this case, and then prop just tells me what is the proportion. Are we saying for the alternate that it is a greater than, a less than, or a not equal to? In this case, it was greater than, right? We want to show that the actual parameter is greater than the null proportion, so we clicked that one. That gives us our z-test statistic. It also gives us our p-value. But let's say you wanted to do it by hand, or in a particular multiple choice or free response question, they ask you just give me the test statistic for this thing, right? And then they say, use the test statistic to calculate the null proportion. You could do, or to find the p-value, right? They can do that. They often do. I often do. So be ready. You go in, you calculate your test statistic. What we do for proportions for test statistics is we do the p-hat minus the null proportion to find the distance it takes to get from the null proportion, which will be the mean of our sampling distribution, all the way out to the fringe where the p-hat sits. We want that distance. We want to divide into that distance the standard error, which is the standard deviation of the sampling distribution, aka how many standard deviations away from my null proportion would my p-hat sit. Right? So I'm going to calculate the standard error. That's what's highlighted in yellow first. That'll be my denominator. I round it up to about 0.016. Notice that for the standard error, you are using the null proportion. Yet again, not the p-hat. The p-hat will only, and I repeat, only legends, appear in one spot, and that is as the first value on the numerator. P-hat minus null proportion. Everything else is null proportion. I found my standard error to be 0.016. I use that as the denominator. I then do 0.56, which is the p-hat that I got from the sample. And then I subtract the null proportion of 0.5 from that. I then divide by the standard error, and I yield about 3.75 as my test statistic. You might have gotten slightly higher or lower. Just show your work. We then went through and figured out how to obtain a p-value from that. We looked at our three options, depending on if we thought it was a higher, more extreme, a lower, more extreme, or simply either end of the extreme, which would be a two-tailed test. In this case, it is a parameter is greater than situation. So we're expecting the high end to be where our p-value sits. So we're going to make the low bound the z-score we just found, the test statistic, and the upper bound will be 100,000. We want to find everything more extreme to the right. And then the mean was 0 and the standard deviation is 1. But of course, we have different ways of doing it for different ones, and we went through all of those. I got a p-value of about 0.0001. You might have gotten a slightly different one, and that is okay, right? Different strokes, as they say, for different folks. And whatever way that it flowed for you, as long as you rounded correctly, I'm sure it's correct. What you will then do is you will compare, and this is super important. In your final part, you will make your conclusion. Your conclusion is where you compare the p-value to the alpha. The alpha is your gate, it's your threshold. You need your p-value to be lower than the alpha to reject the null, and therefore successfully show that the alternate hypothesis has convincing evidence. And in this case, that proved to be what happened. Our p-value was smaller than the alpha of 0.05. Therefore, we rejected the null, and we stated we have convincing evidence for the alternate hypothesis, and in context, that means we have convincing evidence that a majority of US adults support nuclear arms reductions. Okay, heroes, you are incredible. I am so proud of you, and I'm so proud to be your teacher. Make sure. I'm going to say this right now. Look at slide 18 on 7.2. Make sure you're clear on what the probability of a type 1 error is, right? The probability, I will state this one more time for the cheap seats. Oh no, come back. The probability of a type 1 error. Remember from class, type 1 error is alt person, someone who is always rejecting the null in favor of the alternate, even when maybe they shouldn't. And not even maybe. For a type 1 error, you did it when you shouldn't have. You're always jumping around. The probability of a type 1 error equals your alpha, significance level, same words. So that 5%, right, that alpha of 5%, that is the percent of the time that we receive a type 1 error. We reject the null incorrectly. It's possible, right, because we're not 100% sure. On the other hand, the probability of a type 2 error is equal to 1 minus your power level. And on the other way around, right, your power is equal to 1 minus the probability of a type 2 error. Remember, a type 2 error. If type 1 is alt, type 2 is old person. They will not let go of their ways. It is when you fail to reject the null when you should have. Now, this should make sense. The power are the odds that you successfully reject the null, given that the null is false. Type 2 error is when you unsuccessfully reject the null, which is to say you don't reject the null when the null is false. So they are complements one to the other, right? Your power is what's left on the other end of the type 2 error, right? Because in both a type 2 error situation and a power situation, you are assuming, right, that the null is false. Power level is if the null is false and I successfully reject it, that's your power percent. If, on the other hand, the null is false and you don't successfully reject it, those are the odds of a type 2 error. Okay, heroes and legends, I am proud of you. We've gotten through everything. Make sure to go through these notes and know them inside out and backwards. Reach out with questions as often as possible. I am so proud of you. We are railing through some of the hardest material of the year. It just gets uphill from here, but know that everything from these 2 units will glide you through the remainder of the year. I am proud to be your teacher. Keep it up. Keep your nose to the proverbial statistical grindstone. This is Mr. Mays signing off.